So when we look at a system, we compare the energy going in and out of that system to the surroundings. And that can be in the form of heat or work energy. So we get this equation where we say the change in energy of this system is equal to heat plus work. Now, for this course in AP Chemistry, we are largely going to ignore the work energy outside of this immediate context. The work energy has to do more specifically with gases and expansions that push out or if they are compressed. So there is energy in a push out, or there's energy being added if you compress in, which is pushing in. Heat is going to be one of our primary focuses, but we've got this system and surroundings. And we can say that heat going into the system is going to be endothermic, and that is a positive value. We can also see heat going out of the system, and that's going to be exothermic, and that's going to be a negative value. Keeping track of the signs is really important because this can be in words. We could say a heat loss. We could say exothermic. We could say just negative 34 kilojoules. But negative 34 kilojoules and positive 34 kilojoules lost mean the same thing. So you have to watch out for the signs there. Is energy going in or out? Heat energy going in and out of the system. Likewise, work can be done, we say that it is done to the system, and that is when you're compressing it, okay? So we say compression. Work done to the system. We can also have work leave the system, and that's going to be the system pushing out, because when you push something, you're giving energy to that thing you're pushing. So this is going to be an expansion of gases. And that's going to be energy leaving. This is going to be work energy gaining. Okay, so we measure these two things. This is largely related to the volume changes of the gases. And this is really important in this first section here. We talk about pistons and car engines because as the gas expands and contracts, it can move a piston up and down and move a motor and generate electricity. So the work is important for that. But then we say endothermic and exothermic is heat going in or out. So the combination of those two things give us our energy for the system. For work energy now, we have another equation for it because it is related to gases. So this is all relative to the system. The work of the system is equal to negative pressure times the change in volume, negative P delta V. And when you get a final volume minus an initial volume, that's going to be a positive number, so that negative, that expansion will kind of make the signs work, whether you're expanding or compressing. That negative sign is an important part of this. This will come out in units, liters, and atmospheres. And you need to do a conversion to get that into joules. And there's a conversion you can use for that that's actually related, if you're familiar with that number, 101.3. That's related to pascals, which is our SI unit for pressures. So that's going to help us get liters, atmospheres into joules, because that's a unit of energy. So the biggest thing with this equation here is trying to figure out, when we look at a reaction, and our reaction, that's always going to be the balanced equation, is going to be the system. We're going to say, is heat energy going in or out? And is work energy going in or out? It's a combination of both. Thermodynamics gets really, really hard if you go further to your junior, senior level college chemistry classes. Once you start having to incorporate work energy. But when you only have heat energy, we deal with calorimeters, and we're going to start trapping this heat and say, if I can trap this heat, I can measure the heat energy that goes in or out, because we can trap it in something else, and use some heat equations to ultimately figure out what the enthalpy of that reaction is. So we start to standardize it. This is in joules or sometimes kilojoules, and we'll say how many kilojoules per mole will there be, and that's going to give us a new term that we'll talk about later, which is enthalpy. And the units on this are kilojoules per mole. This is just the kilojoule term. Q is kilojoules or joules. This is per mole, so this is a little bit different over here. Okay, but this is essentially what's going on in section 6.1 and how we look at the system and surroundings with heat and work to get the total energy change of the system.